thank you all for attending this morning. I'd like to thank InDesign for organising this event. I'm sure you'll find the CPD presentations really valuable. So my name's Ross Baynham. I'm the National Specification Manager for Alspec. Alspec are one of the country's largest aluminium system suppliers. We supply a range of different products, be that windows, doors, shower screens, balustrades, security screens. Today, we're really going to be talking about windows and doors. The presentation is about understanding Section J NCC 2019 and how that relates to windows and doors. So if you have any questions throughout the presentation, please ask them through the Q&A section, which you'll find there's two like voice boxes. Select that and ask your questions through there. Unfortunately, I'm here by myself today, so I will be answering the questions at the end of the presentation. So for your refuel CPD point, you do need to stay for the whole hour, unfortunately. The questionnaire, hopefully you've all downloaded the questionnaire already. If not, it can be downloaded from the registration page. So that's indesignlive.com/CPD live. So if you go there, you can download them at any time. You can still download them now or even after the presentation. You should receive your participation certificate, your refuel CPD point, within a week. So I think that covers it all. Oh, actually, we will be having a live poll throughout the presentation. So please look in your chat box for a live poll. I'll tell you when that comes on. So the presentation itself is about the performance requirements of Section J, and it's about understanding where it applies. So we're going to look specifically at the U values and solar heat gain coefficient, and we'll be looking a lot at the window to wall ratios, which becomes an important factor in Section J NCC 2019. We'll be looking at some component performance, be that windows, walls, spandrels. We'll also take a look at shading and how that impacts overall performance. We will spend a bit of time looking at some models and how facade performance, be that windows, walls, doors, affect your overall performance and how that might impact your window to wall ratio and designs moving forward. We'll look at some examples of some buildings that have currently already been built, and finally we'll look at some solutions. Okay, so I will make a start. So I'll start with a little bit about Alspec. Alspec are one of Australia's largest manufacturers of aluminium systems. Started 46 years ago. We are an Australian-owned business, still privately owned. We have extruding facilities in Victoria and Queensland. We have our own R&D team based in Queensland as well, with our own NATA accredited testing facility. So we do all of our own in-house testing. We also do all of our own in-house design work as well. So we do a lot of bespoke systems for people. We have design teams based in both New South Wales and Queensland. As you can see from the map there, we're a large business. We employ a lot of people. We have branches all around the country, which I guess is why we are one of the most highly used products, because we service our customers so well. So the learning outcomes are listed there. I won't read through them all, but we're going to be looking at how the requirements apply. We're going to be looking at the performance of windows and walls. We'll be looking at the impact of products on performance, and we'll be looking at how that affects design for future projects. So performance requirements, this section from the National Construction Code hasn't changed. You can still meet the performance requirements via either a performance solution or deemed to satisfy solutions. So JV3 reference building method has been used a lot over the years. It has changed ever so slightly in that it now includes annual greenhouse gas emissions rather than just energy consumption. and there is a thermal comfort target within there as well. Other performance solutions are now available as well, Neighbours or Green Star, so JV1, JV2 respectively. But a lot of what we'll be looking at today is deemed to satisfy. I've highlighted building classes. There are now some distinct differences between building classes, and it all really comes down to building use. Is the building going to be used 24 hours a day like a hotel, or is it going to be an office building that's only used, you know, during working hours? If it's going to be used 24 hours a day, then the energy efficiency requirements are going to be much higher. So we just need to be aware of that when we look at the requirements. So the performance requirements, as you can see there's now a quantifiable level of performance for buildings within a conditioned space. So you can see for, you know, F1, class 6 building, 80 kilojoules per meter squared per hour. The important thing to remember that Section J is being rewritten in its entirety. So the modelling shows that buildings could use could see a 30% increase in energy efficiency. So when we look at the requirements and people consider them to be difficult to meet and really quite stringent, that's by design. It's supposed to be a lot harder to meet because we want more energy efficient buildings, and that's the purpose of Section J now. So the change is based on the principle that overall facade performance is more important than the individual elements. So it's broadly based on the values in the US Energy Code, but that's not really relevant here. The total system U value is calculated as an area weighted average of the total system U value for each component. So you take the U value of each component, area weighted average, and you get the overall U value for the whole facade. You can see here some of the U values listed. In section B there, you've got climate zones 2 and 5, a U value of 2 for particular types of buildings. So this can be done by either, there's a couple of different methods. It can be done by either calculating each aspect separately, so you calculate north, east, south, west separately, or you can do all directions at once. I guess it's just which is easier for you. I put up a pretty simple model here. It's a window to wall ratio of 10%, and that's what it's trying to. We're talking quite a lot about window to wall ratios. I just wanted to highlight what that looks like before we start the presentation. There's a window wall ratio of 50%. It's just to indicate that it's just to give you a visual idea of what that's going to look like when we start talking more about the percentages later. So wall performance, where there's so we've got a U value for the whole facade system, but there are some areas we need to look at individually, and wall performance is one of them. So where you've got a wall performance of less than 80% of the window wall construction, there's a backstop minimum R value of an R1. So if you look at that, you think of a mainly glass building with spandrel panels. So if them spandrel, the wall system is less than 80%, there's a backstop minimum of R1. So just got to consider that when we start looking at spandrel panels. So if the wall is over 80%, the minimum is in the table on the screen there. So think of a big box retail store, convenience store type of building. More than 80% of the facade is wall, therefore you'd revert back to this table for your R values rather than looking at the U values that we're going to be talking about today. Spandrel panels are an interesting area within Section J. I don't think they've been particularly well done over the years. They've been not well detailed and not well insulated. A bit of an afterthought in certain aspects. So in the National Construction Code, they've detailed some configurations of performance values of various spandrels. As you can see from this table at the bottom, you really need a thermally broken spandrel panel to meet a R1. Now, if we go back and suggest that there's a minimum backstop of an R1, it means that your spandrel panel needs to be thermally broken. There are ways around that by of overall design, but in most instances, spandrel panels are going to have to be thermally broken. So adding to the increased requirements for window wall U values, there's also a very strict guidelines around solar gains. So this is a table showing the solar heat gain coefficient requirements. So it varies by building type. If you look here, you can see that in climate zone 6, an office can have a total SHGC, solar heat gain coefficient, of 0.13, whereas an aged care facility in climate zone 6 would have a SHGC of 0.07. It's very, very low. And that's by design. So this is going to be really important when we start calculating windows, walls, glass, etc. Shading is going to become more and more important for your buildings. Obviously, solar heat gain coefficient can be affected by the amount of shading over the facade. We'll go into that with some more detail later, but the things we need to consider are the length of the projection and the height of the windows, how that projection is going to sit over the window. There are some specific requirements. Manually operable shading devices are not counted in the National Construction Code, whereas a shading device that is automatically operated by the sun, and where the sun moves, if it's automated louver system, then that can still be used. But the majority of what we're looking at here is fixed shading devices, essentially. So how do we calculate performance? So the ABCB has released a facade calculator to assist in calculating the overall performance values and total SHGCs. By calculating the weighted averages of the component performance criteria, it's by doing that. So look, essentially you've got a glorified spreadsheet, a glorified Excel spreadsheet, and you put your inputs of U values, SHGCs for your various different performance, and you put the weighted averages in there, and it spits out a value. This would probably be used early on in the process, early on in design, to work out what your U value requirements will be. So if you have 50% wall and you're going to use a particular type of insulated panel system, you'll know what your U values for that will be. You'll be able to calculate via this tool what your U value requirements are going to be. So then you can start looking at what product types you might want to use. There is some confusion and some debate around how you input information into the tool. And it's really around WERS ratings. So people are debating whether you should be using WERS ratings to calculate total system U values, as they only calculate the values based on standardized sizing. And you should really be using actual sizing of products. So the glazing component usually performs better than the frame. So the larger the window, the lower the total U value. If you're using large doors, we have some systems where you can have a 3-meter high door by 2.5 wide panels. They're going to perform better than anything tested in WERS because you're using much smaller systems. However, you're not taking into account with WERS subheads and subsills on your system. So you sort of got swings and roundabouts a little bit. The larger the window, the better it's going to perform, but you're not taking into account subheads and subsills. In reality, it's not going to make that much difference when you're calculating the performance. It'd be a minor change. So what's inside a frame? And I might just get Sophie in the background there to run the live poll, if that's possible, please. So we're looking at the images here. We're looking at two different types of frames. We've got a standard aluminium frame on the left-hand side, showing a sill, and we have a window head system on the right hand side. The left hand side is all aluminium from inside to outside. On the right hand side, you have a thermal break across the middle of the frame. So that's across the subhead and across the head of the frame. What you've got in there is you've got a polyamide strip, which is essentially a plastic strip which runs between aluminium on the outside, aluminium on the inside. Aluminium is a very good conductor of heat, and the polyamide strip, the thermal break in the middle of it, reduces the level of heat transfer from inside to outside or vice versa. This is what it looks like as a thermal model. So the non-thermally broken version of the window head on the left-hand side, and a thermally broken version on the right-hand side. Same temperature ranges, but what we've seen here is the temperature difference on the thermally broken version from inside on the right-hand side to the outside, which is on the left-hand side of each of the images. You've got a 10-degree difference on the thermally broken version, whereas on the non-thermally broken version, you've probably got a 4-5 degree difference at best. And we can see that on the sill as well. Same correlation. You're getting a much larger degree of thermal difference, which means you're keeping heat within the building in a thermally broken version. You're allowing heat to escape on the non-thermally broken version. So the thermal bridging look like in a wall. So this is on the left-hand side there, you see a SC sheet clad wall, timber frame, residential building, and you have batts, fiberglass batts within the stud cavities. The insulation's doing its job. The problem you've got is that from the outside, you can see the heat escaping through the timber studs via the thermal image camera. To reduce the level of thermal bridging in a wall system, you reduce the level of thermal bridges. So here we have, on the right-hand side, we're looking at an insulated panel. As you can see, that covers the frame 100%. You have no thermal bridges with a system like this because you have continuous insulation. So just before we step into some models and some examples of overall facade performance, I'm just going to take you through some typical window and wall systems. Now, the window systems get a little bit complicated because a window system performs differently depending on the type of window or door system it is. And I'm using this to show you that. So a fixed frame window, like you have in the middle, as you can see from the U values at the bottom, performs considerably better than a operable window, an awning window, say. As you look at the figures at the bottom there, you can have a fixed frame system with a thermally broken. You get U values as low as 1.9. These aren't specific products. These are general figures, and we do have systems that can go lower than that. I've seen them as low as 1.6. But for the purposes of this presentation, I'm not specifically talking about any Alspec products here. I'm just talking about systems in general. You revert over to the awning window, as low as you're going to get is probably around that 2.8. You might get slightly better than that, but there's quite a big difference between them. And the reason for that is the amount of aluminium that's around that the window sash. So essentially, you've got double the amount of aluminium. The aluminium doesn't perform as well as the glass in most instances. Therefore, the more aluminium there is, the less the performance of that overall system. And a sliding door sits somewhere in the middle of them. You have more aluminium than you do on a fixed frame, but probably not as inefficient as an operable window. So when we look at typical systems, I'm using typical systems in our models to try and show performance. But as I said, I'm not trying to be specific here. I've made some assumptions, and the assumptions are that there's going to be no poor quality glazing allowed with NCC 2019. So the standard systems, we're going to be looking at standard systems better systems and best systems throughout the models. Now, I'm trying to take an average U value. So I've taken 3 types of window door systems and averaged out the U values for them. The standard system is a non-thermally broken with decent glass. It's not poor glass. I'm not assuming that people are going to use poor glass anymore. There's going to be no single glazed, standard frame systems being used in most commercial. The better systems are thermally broken with a good glass. The best systems are a thermally broken frame with a high performance glass. So you're looking at low E coats, center of glass U value of 1.3. So the 3 U values I'm looking at are 3.9, 3.2, and 2.3 for the various Windows systems. And as I say, I'm calling them standard, better, and best. Similarly, with the wall systems, we've got a standard, better, and a best wall system. So the standard system is essentially what you'd see on most buildings. You've got a steel frame and you've got decent insulation. Nothing wrong with the insulation. The problem is you've got lots of thermal bridges. In NCC 2019, 4859 has changed so that you're now taking into account thermal bridging. So any thermal bridges across your wall system have now been, the overall performance is downgraded massively. So what you're using an R2.7 bat in there, the actual performance is an R1.2. So equivalent U value 0.83. Bear in mind, even a poor performing wall or an average performing wall like that still has a good U value in comparison with windows and doors. We do have to remember that walls are always going to perform better than your glazing components, which is why people are trying to reduce window wall ratios. So the better performing wall systems, you've got a concrete wall type system with a continuous insulation. This is a rigid board insulation, good high performance product, very minimal thermal breaks, but there are a few, obviously, for your fixings, but not really. You ended up with a U value of 0.4, so good performing wall. And the best type of systems, you're looking at insulated panels. This is an R4 insulated panel. You get your U value down to sort of 0.25. Obviously, that's not applicable for all type of buildings. You're not going to be able to use that on all building types, but it shows what's possible. So we're going to run through a few of these slides now. Please don't switch off. There's about a dozen of them, but I think they are important, and I won't dwell on them too long. The purpose of these is just to show what levels of window to wall ratio you can start to consider for various different system types. So this is just an example. This is not one of the. This is looking at a poor window system. Now I say poor window system. It's essentially what's being used for most of Australian commercial buildings for the past decade. So you're looking at a U value of 5, and this is a better wall system. So this is a mid-level wall system, R value 2.5. I want to explain the graph for you to give you an understanding of what we'll be looking at. So the 2 lines that run across are the U value of 1.1. So that's an aged care facility in Melbourne, and U value of 2 is an office building in Sydney. So we can use them as 2 examples, and the line, the U value line. So if you have a 0 window to wall ratio, that means you've got the whole facade is wall, and then you've got a U value of 0.4. So very good performance, of course, but you've got no light coming into your building. On the other scale, at 100% window to wall ratio, you have a U value of 5. So not very well performing at all. Clearly, it doesn't meet the requirements of either of them buildings. So where the intersections are, so if you were to build an aged care facility in Melbourne with these 2 systems, you could have a window wall ratio of about 15%. And if you were building an office building in Sydney, about 35%. So hopefully that explains it, because we're going to run through a few of these. So this is a standard window, standard wall. As you can see, with a standard window system, you are very, very limited to work on an aged care facility in Melbourne, because your window to wall ratios 10%. So really not that great performance. You jump up to a better wall system, you're up to about 20% with the in an aged care facility in Melbourne, and an office in Sydney, 45%. I'll just jump through these. The best wall system doesn't change the overall performance that much. So there's a combination. The standard window is not getting you greatest performance in these. And bear in mind the standard, I'll just remind you that the standard window system we're looking at is a non-thermally broken, decent, okay, double glazed unit. So the wall system isn't affecting the performance too much. You know, your range on a standard system there for an office building in Sydney, you're looking at sort of 35 to 45% window to wall ratio, depending on your wall. So the wall's not affecting it too much. You use a better window system, and you know, you're looking at thermally broken product now. Your aged care facility in Melbourne's still very, very difficult. You're only a bit over 10%, whereas your office in Sydney around that 50% mark. And then you move to a better wall, changes slightly. You can use you're up to 25% for your aged care, and only a slight adjustment for your best wall system. So in combination, once again, the wall is not making that much difference. It's the lowest common denominator here is the window system, and so the poorer part of the performance of your facade is making the bigger difference. You know, changing your wall system, you're only going from 45 to 55% window to wall ratio in your office building in Sydney. However, you look at a best window system, so a U value of 2.3, and you immediately, even with a standard wall, your Sydney office building, you're already up at almost 80%. And the reason for that is you're almost meeting the requirements just with the window alone. So the performance requirement is U value of 2, your 2.3 with the window. So changing the wall system doesn't affect the window to wall ratio too much in Sydney, but you can see it affects the aged care in Melbourne a bit. So you look at them comparisons, you're up at a bit over 40% for your aged care facility in Melbourne with the best type of window system and the best type of wall. So that's workable. You've got a system that you can work with there. We'll just look at an extreme wall. So this is, I say an extreme wall, you're looking at an R6 sort of insulated panel probably. They're available. It's a 140mm panel. I've seen them being used. Reality is, doesn't affect the overall performance too much. It's the various window types that are affecting the performance. Even with an extreme wall, you use a standard window. For your office in Sydney, you're at about 50%, and you use the best window, you're up at 85%. So it's the window that's making the difference, not the wall. On the other side, you use a extreme window, and I say extreme window. It's considering how you design your buildings. So they've used the term extreme window. These are possible, and these are absolutely available. The problem is it's using more fixed framing rather than operable framing and sliding doors. Limit the size of your sliding doors, possibly limit the size of your operable windows, have more fixed framing. As I said previously, we've got systems where you can have a U value of 1.6. So it is possible to do this. And then, of course, if you've got a U value on your windows of 1.8, well, you can use 100% of it in an office building in Sydney because the requirement's only 2. It doesn't matter what you do with your walls; you're always going to be better. Even then, you still need to consider how you design an aged care facility in Melbourne, because the performance requirements are really low, and that's by design. They don't want glass aged care facilities. The National Construction Code has been designed to ensure that we have a practical and usable window to wall ratio. So solar heat gain coefficient is another performance metric that needs to be really considered here. So solar heat gain measures heat through windows on by sunlight. So solar heat gain coefficient is expressed as a decimal between 0 and 1. Essentially, the lower a window's solar heat gain coefficient, the less solar it transmits. That's the standard definition. Now, with the new standards, solar heat gain coefficient needs to be considered for the whole window wall construction. So just consider lots of walls means not much solar gain. Lots of windows means lots of solar gain, essentially. We're just going to look at a few standard glass solar heat gain coefficient values. So standard clear double glazed unit, you're looking at a solar heat gain coefficient of 0.71. Even with a super grey, dark glass, low E, high performance, your building's going to look a bit like the one on the bottom there, very, very dark glass. You've got a SHGC of 0.16. I'll just remind you of the values that you need to meet in your buildings. Remember, with essentially the best type of glass you can get, you're at 0.16. So in an aged care facility in Melbourne, you need 0.07. So the requirements on SHGC are even more onerous than the U values. But well, I'll come to how we can get around that. So this is the comparison. So once again, similar to previous, the requirements for solar heat gain coefficient in aged care facility in Melbourne is the yellow line across, and office tower in Sydney is the blue line. A decent performing SHGC at 0.27, you're looking at almost 50% window to wall ratio. In an aged care facility in Melbourne, you are looking at less than 30%. If you're using clear glass, well, you're down at less than 10% for an aged care facility in Melbourne, less than 20 for an office in Sydney. So it's not going to be easy. But what they don't take into consideration is shading. So the different types of shading that you can use, as I previously mentioned, operable shading is okay to use as long as it's automated, as long as it's solar controlled. What they don't want is human error, where people don't move the operable shading. So there's a variety of different types of shading you can use. You've got horizontal and vertical. You've got some screen shading on the right hand side over there. You can use balcony overhangs, like the one on the bottom left. It's got a combination of screens, operable shading, which I doubt that looks manual to me. And then you've got overhangs in there. So there's lots of different ways in which you can operate shading. So shading performance, what that affects. Look, there's a fairly complicated table in the National Construction Code, which I'll let you disseminate yourselves over time. I'm sure you'll find it enjoyable. But the effects are, this is just an example. So look, I've taken a good glass, so a product that's got a solar heat gain coefficient of 0.25. So where there's zero shading, you look on the far left hand side of that, zero shading, you've got a solar heat gain coefficient of 0.25. You move out to a 1 meter projection of shading across that window, and you have 0.18, right up to a 3 meter projection. And bear in mind, this is I think I calculated on a 3 meter high piece of glass. You have about 0.09. So you can't, the shading is not going to completely get rid of your solar heat gain requirements, but it can really help. So good shading is going to be vitally important moving forward. I'm just going to take you through some projects and just have a look at how buildings might change. And look, I'm sure you all have, you're all experienced architects and designers. I'm sure you all have wonderful ideas about how you will meet the requirements moving forward. But I just want to look at a few examples and I guess start people thinking about what they're going to do with their buildings. So these projects I'm looking at are projects I've just pulled off our website. So off the Alspec website, these are projects that have all been completed. They were all completed prior to NCC 2019, obviously. So we'll start off with a couple of education projects. There's the AB Patterson College in Queensland. On the left-hand side, about 60% window to wall ratio being used here, minimal shading. Now, look, I'm not going to go into the details of what systems were used, because you can safely say that most of them were fairly low-performing glass and non-thermally broken aluminium framing. Some of them will have decent glass. That's not fair. But we don't need to go into the specifics. I mean, the point of this is to try and work out what you could do with a building like this to meet the current requirements. So you'd have a solar heat gain coefficient of requirement of 0.13 and a U value of 2. Probably in a building like this, you could do that. You could meet them requirements, but you would need to increase the performance of the framing. You'd need a thermally broken framing, probably a decent high-performance glass, and you'd need considerably more shading than what's been on offer here. Essentially, the shading isn't going to be sufficient to meet your relatively low U value, SHGC values on that building. The Pridham Hall at the University of South Australia, beautiful looking building. Problem is it's mainly glass. It's a problem from a solar heat gain coefficient point of view, because the shading, that what looks like a large projection is projecting upwards quite a bit. So I'm not sure it's offering a great deal of shading to the window system there. So depending on how well the spandrel in there is detailed, that might just be coloured glass. If you can put some insulation in behind there and remove the solar heat gain coefficient from the glass with that system, you could do it, but you'd need to increase the amount of shading. You'd have to have high performance glass. It looks like clear glass in there that's currently in there. So there's a few things you could do, but you'd have to have some tweaks on your redesign there. Just looked at some apartment buildings. So the building on the left-hand side in Melbourne, very low window to wall ratio, probably only about 25, maybe 30% window to wall ratio, deep shading on a lot of them with the balconies. So look, that would be in a good position to still currently meet the requirements. I mean, obviously depending on the type of glass that's being used, but that should be okay. A slightly different story with the building on the right hand side, a famous building in Fortitude Valley, but it depends how it's built. I mean, this building, you look at it and say, okay, there's a large window to wall ratio, not a lot of shading, but this could be tweaked very quickly from a design point of view. Some shading devices may be needed, but looking at the panel systems there, if some of them panels are filled in and you're using that as a shading device, so you're turning it into a wall, you could do that. High performance glass, high performance framing, you could meet the requirements. It's just, early planning would be needed on a building like that. Some retail projects, a couple from Queensland. The Coles building on the left-hand side, probably about 50% window to wall ratio, a lot of deep shading. That's in a pretty good position. You would you'd consider that and say, oh, that might be okay. It might be okay with some good framing, good glass. You'd probably be able to meet the requirements without changing the design of that building. The Commons on the right-hand side. Now, the far side of this building is the beach, so you'd want as much of your glass as possible on that side. Because you've got quite a high window to wall ratio on this building, I mean, far be it from me to tell designers how to do their job, but I would probably look at this one and say, look, to meet NCC 2019 Section J, you could potentially put more wall on this side of the building where you're not overlooking the beach on the other side. Maybe have some high performance walls in this side, reduce that window to wall ratio. It's got good shading, so the solar heat gain coefficient requirement could be met. So, I just think a little bit of a retweak on the design there may be sufficient. Then we'll look at aged care projects. Now, these aged care projects are both in northern states, in Sydney and Queensland, so they've not got the very low U value requirements. But the one in Queensland, the Japara job, relatively low window to wall ratio at 40%, a lot of shading. You could meet the requirements with that sort of building without necessarily redesigning. You could increase the thermal performance of the frames and the glass, and you should be relatively okay. A bit more window to wall ratio, higher window to wall ratio on the AVO and Bella Vista. So you've got up to sort of 65% probably in them. Within them deep shaded balconies, you have quite a lot of glass. Might be prudent to change some of that glass to a high performance wall system. It's not great for a company like Alspec to sell less windows and doors, but for the energy efficiency stakes of a building like this, that might be required. So we'll start moving into the conclusions. The better window combinations, and you can start to have an okay window to wall ratio. You're looking at 65% window wall ratio with a better wall system. You can get slightly better than that, of course, with the best window systems. The U values can be met. The challenge from an architectural point of view and a design point of view is going to be a solar heat gain coefficient, probably more than anything. With standard systems and standard glazing systems, you're looking at pretty low window to wall ratio. So you're really going to have to start to consider shading, designs, percentage of window wall. That's going to be where your challenges are. So some of the things to consider when you're starting to design buildings for NCC 2019. I think it's a given that you need to start removing thermal bridging from your walls wherever possible. As we saw from the steel framed wall system earlier, going from a 2.7 bat, as of NCC 2019, we were just looking at insulation, path through the insulation, whereas now you're taking into account thermal bridging. That wall system was down to an R value of 1.2. Reducing the thermal bridgings is a no-brainer. Ensure your spandrel panels are well detailed. You can use a spandrel panel to your advantage. Make sure that it's well detailed and well insulated, and you're essentially going to end up with very good performance from it. So you want to improve the performance of your lowest performing components, and in most instances that's going to be your windows and doors. So your windows, your doors, your fixed framing, ensure that they're performing well, and your overall system's going to perform well. Your window is always going to have less performance than your wall when it comes to thermal performance and solar gain. So introduce shading to reduce solar gains. That's going to be really, really important. You're going to have to start considering that early in your design process. Sometimes you're going to have to reduce window to wall ratio. I think that was one of the intents of the National Construction Code and the ABCB when they put this Section J together. It was to try and reduce window wall ratios, especially in buildings like aged care facilities. ESD consultants, they've always been important, but they're going to be even more important, and you need to contact them early. They're going to be able to use that ABCB calculator to give you some advice. You're going to be able to look at your designs, look at how your shading is going to affect your SHGCs. They're going to be able to start telling you early on in the design process what your U-value requirements are going to be for your windows and door systems. And then, of course, consult your product suppliers. Once you know what U-values you require, talk to Alspec, talk to your system suppliers and your insulation companies, and they'll be able to provide you with detailed information early on in the process to ensure that you get the buildings you want. I mean, essentially, the whole point of Section J is to get more energy efficient buildings, and that's what all your product suppliers are there for as well. So I'd like to thank everyone for your time today. Please feel free to take my details down. We have specification team all around the country. We're more than happy to assist wherever you need. I will just jump into our Q&A and see what we have in there, see if there's any questions before I finish up. The presentation will be, someone's asking, Danilo is asking if we'll share the presentation. Yes, the presentation will be downloadable on the website after. I'm not sure how long it's going to take. I think they said that the certificates would be available within a week. I think the presentations will all be available. I'm not sure if they'll be available within the week, but within a couple of weeks, no doubt. What's the definition of a wall? Include solid element only, window frame included. Is a CFC panel in a window frame wall? Yes. So the definition of a wall would be the solid element. So the frame of a window is not classified as a wall, and the definition is important. But we're looking at performance. So I mean, if you have a CFC panel in a window frame, whether it's a window or a wall, the actual performance of that system is the important thing, Alan. So look, I'd consider the overall performance of it. If you're putting a CFC sheet in a window frame, that's cool, but make sure there's plenty of space in behind it for insulation, and then you can detail it well enough. As I was mentioning about detailing spandrels, if you detail that well, it becomes a wall from a performance point of view, whether from the outside of the building it looks like a window or a wall. It doesn't matter too much in that sense. Does Alspec have any passive house certified systems? No, not specifically. No, we don't have passive certified products, but we could certainly provide our high performance systems could be used in passive house buildings. Edward, I'd be more than happy to talk to you about that. Is the thermal break in a window certified as non-combustible? No. So there is an exemption within the National Construction Code for thermal breaks for non-combustibility. Essentially, you can't get a non-combustible thermal break. All of our systems are aluminium, but the thermal break part has been exempt from the National Construction Code for 1530 Part 1. Are these percentages based per facade or overall? They were based on overall. You could work either way, whether it's per facade or either or. Sounds like new Section J will lead to Australians living in darker places as they get older. Yeah, potentially. I mean, look, what we don't want is poor poor buildings. We don't want huge amounts of solar gain on an aged care facility. So yeah, I mean, using high performance glass, you can still get decent visible light transmission through them. So you still get light but stopping some of that solar gain. Will Alspec be considering adding XPS strips within the frame to reduce? No. No, we wouldn't be putting XPS strips in. Look, I mean, you're talking about to reduce the air movement. Most of our systems would have baffles through them, so our thermally broken systems would have a baffle in there to stop air movement through the system. So no, we wouldn't be looking at using XPS strips in there. The presentation is building orientation considered. Yes, building orientation is considered. So if you're looking at the if you use the ABCB calculator, it does take the different solar loads for each element separately. So yeah, that's absolutely. Unfortunately, I'm not supposed to answer the question for you, Furio. Why don't they want aged care, glass in aged care? It's not that they don't want glass. I think it's just they want thermal comfort. An aged care facility has people living in it all the time, and the idea is that they don't get too hot in, if you're in Queensland and you've got a building that's going to get a lot of heat coming into it, you don't want it getting too hot. And conversely, in Melbourne, you have hot days and cold days. We want thermal comfort in our buildings. Okay, so I think some people want the answers to the questions. Hopefully, I answered most of the questions as we went through that. If anyone has any specific questions, please feel free to contact me directly. My contact details are there. Otherwise, I thank you all for attending today. There are some more great presentations throughout the day. Hopefully, you found some value in that. And I wish you all a good day. Thank you very much. Oh, sorry, one last thing. I just wanted to share our poll. So have you used a thermally broken aluminium framing on any of your projects in the last 12 months? So it turns out that only 25% of people have. Well, it's good that 25% of people have. There seems to be a lot of movement. So there's a lot more projects that are going to be designed with thermally broken framing. So interesting that 75% of people haven't. I think if we did this in 12 months' time, I think we'd probably see a slightly different answer. But it's interesting to see the details there. Okay, thank you all.